Hey everybody, so today we're going to talk about neutralization reactions. We need to be able to calculate the equivalence point. We actually need to be able to calculate quite a bit at the equivalence point of a reaction. First, we have to know what it is. Secondly, we have to calculate the amount of acid and base necessary to reach the equivalence point. And third, we have to be able to calculate the pH at the equivalence point. We're also going to learn how to look at a reaction in which we've added extra acid or base past the equivalence point, and how to take the pH then. So first off, what is neutralization? Well, it's the type of reaction where an acid and a base are added to each other. The acid and the base react, and the products of that reaction are water and salt. Since water is neutral, that's where these reactions get their name. Important to note though, when we have a solution in which we have acid and base added to each other, it's not always going to end up being a neutral solution. So it's not called a neutralization reaction because you always get a pH of 7. It's called a neutralization reaction because we're adding acid and base together and we get some water out of that. Okay, so the equivalence point is a very important thing in acid-base reactions. So it's the point in the reaction in which the amount of acid is equal to the amount of base. So at this point, the solution is salt water, it's products. So if I have an equal amount of acid and base, what happens is they react and they form the products, they form the salt and the water. What does this look like when we have an acid and a strong base? Well, we know that the acidic part of an acid compound is the hydrogen. We know that with a strong base, which again is an alkaline or 3 of the alkaline earth metals with hydroxide, so hydroxide has to be a part of a strong base, that those two things react together and they're going to form the product water. The remaining ions would actually be spectator ions, and so in a net ionic equation we actually wouldn't even put the other ions, but they are what forms that salt. So the ionic compound that is formed from the cation of the base and the anion of the acid, that is a salt. And again, usually it gets taken out of net ionic equations, but you'll see it in full chemical equations for strong acid, strong base reactions. With weak base reactions, it's a little bit different. So many of the weak bases are not your typical Arrhenius bases. They don't have hydroxide. So we're not going to see the water product there. What we're going to see is that proton transfer. So remember what happens in a Bronsted-Lowry reaction. So when we have a Bronsted-Lowry base, the acid loses that proton, aka hydrogen, and the base gains the proton. So what we end up with is the conjugate acid, right, that has the extra hydrogen on it, and the conjugate base. Oftentimes they'll combine those two and show you the formula for the salt because you have a positive and a negative ion here. They'll put them together and give the formula for that salt product. So oftentimes that's what those look like whenever you have the Bronsted-Lowry bases that don't have hydroxide. And that's what we have in this example. So in the example that we have in the notes, we have to calculate the amount of acid required, so the amount of hydrochloric acid required, to neutralize 50 milliliters of 0.25 molar methylamine CH3NH2. Now, they gave you a KB here for this, which we're going to end up using later, and also we're going to look at that as a hint in a second. We have to calculate the pH of the solution at the equivalence point. So first, when reading these problems, it's important to understand the parts that you're dealing with. We have to look at the formulas that we were given for our reactants and identify the acid and the base, and write the balanced equation for the reaction. This is a really important step because we need to understand how protons are moving around. We know that they need to leave the acid and go to the base. So it's really important that we identify them. That way we write these equations correctly. Obviously HCl, it's called hydrochloric acid. We're familiar with it. It's a strong acid. So that's the acid. This other compound, methylamine, it does not have a hydrogen at the beginning of it. Instead, it has the hydrogen at the end, which is often something common to those organic weak bases. Also, they gave us a KB value, so kind of a dead giveaway. That is going to be the base. So when we write this equation, what we have to do is we have to take the acid and the base, and we have to show that proton transfer. So it's going to leave the acid and go to the base. For organic bases, you put that hydrogen at the end. So that extra hydrogen is going to go at the end. So what we're left with is chlorine, the conjugate base, and the ion for the methylamine, CH3NH3 positive. Now again, we could put that together and we could write the formula for that salt. So it would be CH3NH3Cl. We could just put those two parts together. What we're going to do is we're going to use what we know about aqueous solutions and molarity to determine how many moles of known we've got. So remember, there's a relationship between moles, molarity, and liters, right? We actually were given milliliters in this problem, and so we're going to keep the milliliters and end up calculating millimoles instead of moles. Why? I just don't feel like doing extra conversions. So when you're given milliliters, it's okay to keep it milliliters. Just be aware that you're not calculating moles at that point. You're calculating millimoles. So milliliters, go with millimoles. Okay, so looking back at the problem, there was a ton of information given to us. Again, if I look at the triangle, I need two pieces of information to calculate the third. For hydrochloric acid, all I was given was a molarity. That's it. So I really can't do any more math with that. For the base, I was given both a molarity and a volume. So those two pieces of information were provided. I was also given a KB for that, but that's not part of what we're doing right now. So I'm really just going to focus on the milliliters and molarity of that base that I was given. So what we have is we have the molarity of 0.25 molar methylamine. We're going to multiply that, because these are next to each other, by the volume, which is 50.0 milliliters. And that's going to give us 12.5 millimoles of base. Then what we need to do is determine the volume of the unknown, in this case hydrochloric acid, necessary. So remember that at equivalence, the amount of acid has to be equal to the amount of base. So we can use that triangle again to figure out how much of that acid we need. So if I have 12.5 millimoles of base present in my solution, then I need 12.5 millimoles of HCl to neutralize it. So I know how many millimoles I've got. We were also provided with the molarity of the hydrochloric acid in the problem. So if I take the millimoles and divide it by the molarity, which was 0.10, then what I get is milliliters. So again, millimoles is going to give me milliliters here. And 12.5 divided by 0.10 is 125 milliliters. So it's going to require 125 milliliters of that 0.10 molar hydrochloric acid to fully neutralize the base. It's a really important note to keep in mind that the math on this works the same with weak bases as strong bases. It doesn't matter that it's a weak base or strong base. It just matters that the amount of acid is equal to base at the equivalence point. So there is no mathematical difference in calculating the equivalence point of a weak acid or strong acid, weak base, strong base. You just have to make sure that the amount of acid is equal to the amount of base. So the alternative method is to, since we know we have to have equal numbers of moles of each, is to set the calculation of moles for the acid equal to the calculation of moles for the base. It looks like a modified dilution formula. So we can just plug in the information that we have. The molarity of the acid was 0.10 molar. We actually didn't know the volume of the acid, but we do know that in the chemical formula, there is one proton that could dissociate. So 1 is going to go there. We set that equal to the molarity of the base, which is 0.25, the volume of the base, which is 50.0 milliliters. And then there actually are no hydroxides in this base. So another way to think about this is for those Bronsted-Lowry bases, it's the number of protons accepted. So when this base did its base thing and accepted a proton, it accepted a single proton. So we're going to drop a 1 in there. And so again, you could just do the math on this. You just use algebra, solve for VA, and so the volume of the acid, again, if we solve for it, would be 125. So you can shorten this up by using this chemical formula here. Okay. So now what we have to think about is we know how much it's going to take to neutralize this solution. But at the equivalence point, we have salt and water. What we have are the products. And if I think about this salt for a second that we made, if I go back and look at the salt that we made, the salt is methylamine chloride. And so that is a salt that contains the ion of a weak base and the ion of a strong acid. So again, if I put these two together and write the formula for that salt, it's CH3NH3Cl. That would be the salt. When I take that salt apart and examine the cation and anion separately, what I notice is that the cation is the cation of a weak base, that the anion is the anion of a strong acid. So what we would expect is that since I have a strong acid ion in this solution, that the pH is going to be slightly acidic at that equivalence point because the salt is an acidic salt. So it's not going to be 7 when we hit the neutralization point, when we hit the equivalence point. Instead, it's going to be slightly acidic because the salt that we're creating as a product of this reaction is an acidic salt. So what we're going to do is write the equation for the hydrolysis of that salt. Okay, the salt, again, was that methylamine, it's a mouthful, CH3NH3Cl. Now, when we're writing equations for hydrolysis, the strong ion, because it dissociates 100%, that's the definition of strong, is going to be removed from the equation because it's a spectator. And so then it's the weak ion that starts off our hydrolysis equation, and water. And what we have to do is, if this is an acidic solution, we have to move that proton. It's going to become CH3NH2 again, and then that proton moves to the water, so the other product is hydronium. So that makes sense. This is an acidic solution, so we should end up with hydronium. Now, the issue with this is that in order to find the pH, since this is a weak base, weak acid solution, we would need to use the equilibrium constant, right? Now, Ka is for acids, and Kb is for bases. We know this. When we write this equation, we're going to be using a Ka value because this is an acidic solution. We have H3O plus as a product. We predicted that this was going to be acidic. So I'm going to write my Ka expression. Ka would be equal to my products, which is CH3NH2 and hydronium, over my reactant, CH3NH3 plus. Again, leave water out of your Ka expression. The issue with this is that although this is an acidic equation, I'm writing a Ka expression. The value that was given to me for this substance is a Kb value. We can't use Kb when we need Ka. Luckily, it's really easy to convert Kb to Ka using Kw. So that Kb value is 4.4 times 10 to the negative fourth. So I'm going to take my Kw, which is 1.0 times 10 to the negative 14th, divide it by Kb, which was 4.4 times 10 to the negative fourth, and that's going to end up giving me my Ka value. And so Ka for this one is 2.3 times 10 to the negative 11th. So now I have that value that I can substitute into this expression. So 2.3 times 10 to the negative 11th is the Ka value. since we have to find pH, we don't know how much of this actually formed products. We don't know how much, how forward this hydrolysis equation actually went. So I don't have these values on top. Those are going to be my x's, right, which is eventually going to be x squared. We have to figure out the concentration of the salt at this point. So we have to take what we know about this reaction that happened, this acid-base reaction, and figure out how much salt is in this solution. So this is a whole other thing that we have to do. Let's think about what we did, right? So what did we do? We took this base, which we calculated we have 12.5 millimoles of, right? We added 12.5 millimoles of that acid. We know that we lose on this side and we gain on this side because there was no product at the beginning. And these reactions typically go to completion. So we're going to use up as much of the reactant as possible. So if that happens, and I add X to each of these, I'm going to take as much as I can from here, which is going to be the full 12.5 millimoles, right? And add it over here. And so I end up getting 12.5 millimoles of the chloride, which is a spectator we're not worried about. But I also get 12.5 millimoles of that methylamine conjugate acid. So I have 12.5 millimoles of this ion floating around. Again, Ka and Kb isn't based on moles, it's based on molarity. So that's how many moles I have, but it's floating around in solution. How much solution? Well, we started with 50 milliliters of the stuff in the problem, and then we calculated that we would have to add 125 more in order to neutralize the solution. So if I had 50 and I added 125 more to neutralize it, I now have 175 milliliters total of that acid. So to figure out this number right here, right, the concentration of this ion, I have the 12.5 millimoles of it that were created in the reaction divided by the 175 milliliter total volume of the acid and base added together. And so that together is going to give me a concentration of 0.071 molar. So that's the number that's going to end up going in there. So this becomes 0.071. We need to multiply that times the side of the equation. And then since this is x times x, this becomes x squared. We're going to solve for x by taking the square root. So when we find x is equal to 1.28 times 10 to the negative 6. That's the molarity of both the CH3NH2, the methylamine, and also the hydronium that's floating around in this solution. And really, since that's the concentration of hydronium, right, what we can do is we can negative log that value and get the pH. So when we negative log that value, we get 5.894. That would be the pH of this solution at the equivalence point. Does it make sense? Yes, that pH is less than 7, and we said that this was an acidic salt. So at the equivalence point, when I have just salt and water, if it's an acidic salt, I should have an acidic pH. And a pH value less than 7 is acidic, so 5.894 is a reasonable answer for this problem. So there's a lot that went into this. First, we had to know the reaction that was happening. We had to calculate the volume of the acid that had to be added to reach equivalence. Then we had to figure out, looking at the salt, whether it would be an acidic or basic solution. Write the equation for the hydrolysis of that salt. Write the Ka expression because it was an acidic salt. Plug in the numbers, and we had to solve for the molarity of the salt first. Plug in those numbers to the Ka expression, solve, and then negative log it to get a pH. So this is sort of a complicated process, but it is necessary to find the pH at the equivalence point anytime you don't have a neutral salt. If you have a neutral salt, you're on easy street. It's neutral, so it's 7. So that makes it a lot easier. But anytime you don't have a neutral salt, you're going to have to go through this process. And it goes on. So oftentimes what happens is you don't add exactly the right amount of acid. So let's say that we overshot the equivalence point, and instead of adding the 125, what we did was we added 150 milliliters of that 0.10 molar hydrochloric acid to the 50 milliliter 0.25 molar methylamine solution. So what we did was we added too much of the HCl. We have to calculate the pH of the resulting solution. Now, if I added too much HCl, if I added an excess amount of acid, then what I should predict is that this is going to be a pretty acidic pH because I have too much acid in it. So go in with an idea. Think about it in your head. If you have too much acid, this is probably going to end up being a pretty acidic solution. So what we have to do is we have to follow steps 1 through 3 to calculate the equivalence point, which we did. We knew that we had to add 125 milliliters to reach equivalence. We've got 150 now. We can set up a rice table to determine the amount of excess acid or base. And in this case, what we have is excess acid. So X is going to represent that equivalence amount, right? Let me go ahead and just write it out so you can see what I mean exactly. So the reaction that we had started with was the hydrochloric acid and the methylamine reacting to form this salt. There we go. What we had at the beginning, we already did the math on this. We took the 50 milliliters and multiplied it by the 0.25 molar. We know that we've got 12.5 millimoles of this to start. And at the beginning, initially, we had no product. For the acid, it's a little bit different now. What we have for the acid is we have 150 milliliters of the 0.10 molar solution. And so that's actually 15 millimoles of that to start with. So I really do have 15 millimoles of that. Now the deal is, this is kind of a limiting reagent problem at this point. It is going to go to completion, but I only have 12.5 millimoles of this. So when I subtract X from this side and subtract X from this side and add X to this side, the maximum amount that I can take away to get 0 is going to be 12.5. So I'm going to take away 12.5 here and I end up with 0. I'm going to add 12.5 here, so I have that 12.5 millimoles of salt. When I take away 12.5 millimoles here, what I end up with is 2.5 millimoles extra. Okay, and so using the excess millimoles of acid, we need to calculate the molarity of that extra acid and therefore the resulting pH. And you can think about this, we've done problems like this before. We have this product, this acidic salt, right, which is a weak acidic salt. So we have a very weak ion here, and we have it mixed with the excess hydrochloric acid. So remember that when we have a mixture of acids and bases, we really just focused on the strongest one. And when we have excess hydrochloric acid, that's obviously the strongest substance in this mixture. So it's going to be the 2.5 millimoles of hydrochloric acid that controls the pH of this solution. We're not even going to worry about this anymore. We passed the equivalence point. I'm not worried about the Ka, Kb because I have a strong acid in this solution. So I'm just going to look at the excess amount of strong acid because that's going to control the pH. I have 2.5 millimoles of excess HCl, which is excess hydrogen, right? It's 100% dissociated. It just gives off those hydrogen ions. Now I have that in a solution that is 150 milliliters of the acid and 50 milliliters of base. So really, I have it sitting in 200 milliliters of solution. Okay, remember you always have to use your total volume of the things that you added together to find molarity. And so if I take that and divide, I end up with a 0.017 molar solution of hydrogen. We just have to negative log that to get the pH. And so if we negative log that, then the pH is going to be equal to 1.78. Does that make sense? Yes. I have an excess amount of strong acid in the solution, so I should have a pretty low pH at this point of the solution. So we really need to think about kind of what's happening here, because next week we're going to get to titrations. And basically, when you have a neutralization reaction like this, it's a titration pretty much. In a titration, what we do is we just monitor the pH at each point. So I'm going to think about, mathematically, if I graph this, how would it look? Well, I would put the pH on the y-axis, and I would have the volume of what we were adding as my x-axis. So whatever you're adding to your known solution, that's gonna go down here. And so we can actually calculate the starting pH of this solution based on the information we were given. For methylamine, if I just have that base in the water, then I can actually use Kb, right? Because Kb would be equal to x squared over the concentration of that base. Since that's the only thing in there, it's the only thing I'm worried about. We could plug the numbers in. We had 4.4 times 10 to the negative fourth as Kb equal to x squared over 0.25, because that was the starting concentration of that base. So before I added anything to it, it was just base. I can just use my Kb expression, right? When I find x, that's equal to the hydroxide ion concentration. And if we actually did the math on that and we found the x value, it would be equal to 0.010. So if you do the math and solve for x, it's 0.010. And so that means if I negative log that, the pOH is equal to about 1.98. And then if we subtract from 14, the pH is about 12.02. So this would be the pH before anything was added. So if I'm thinking about this reaction, 12 would be about here. So before I added any hydrochloric acid, I had a pH of about 12.02 to start with. Now we know that we had to add 125 milliliters of this stuff to reach the equivalence point. And at the equivalence point, the pH was not 7. The pH was a little bit different. We calculated the pH to be about 5.894. So at 125 milliliters, my pH was 5.894. So what happened was we added acid, the pH doesn't change too much, and then all of a sudden the pH drops. And so at that equivalence point, when I have equal amounts of acid and base, the pH of that solution was 5.894. Now remember, we did another problem, right? And we figured out that at 150 milliliters of acid, the pH was about 1.78. So it's really low, it's down here. So as this kept going, eventually this thing dipped down to 1.78. And so what we'll notice is that we get these big curves. And when we start adding acid to base and monitor the pH throughout that reaction, we're going to see big pH changes. It's going to start from one extreme and go to the other. The middle of that curve is going to be our equivalence point. And so using the salt, we can figure out the pH at that point. We can always use the information about our starting solution to calculate its starting pH. And then we can figure out how much excess there is, and we can figure out the ending pH of that solution.